Okay, I think we're live. Hi everyone, welcome to Chem Help ASAP. This is our first live stream. Today we are going to be working stoichiometry problems. So I will work stoichiometry problems for an hour. I'll try to get through as many problems as I can in that hour. We will start with really simple mole-to-mole stoichiometry problems, then we'll move on to gram-to-gram stoichiometry problems, and then I will try and fit as many different other kinds in as I can. So you can already see on the screen I've got our first mole-to-mole problem. So let's first just read our problem. If a solution has 2 moles of silver nitrate, how many moles of silver chloride will form when an excess of sodium chloride is added to the solution? So whenever I am doing really any kind of chemistry problem, the first question I want to ask myself is, what kind of problem am I working here? Because then that will tell me what toolbox to use for working these problems. Now, obviously this is a stoichiometry problem, but how do I know that if I didn't know that I was just working stoichiometry problems? Well, there is one thing that I really look for that will really give you a heads up that you're looking at a stoichiometry problem. And that is that this problem has asked you how many moles of silver chloride, but it has given you information about silver nitrate. So you have been asked about one molecule and you have been given information about another molecule. So what you need to be able to do is to connect those 2 molecules with a balanced chemical equation. So my problem already has a chemical equation here, and this is how we are going to connect the silver nitrate and the silver chloride. Without a chemical equation, you cannot make the connection between the 2. So that is what tells me it is a stoichiometry problem. If ever you're given information about one molecule, asked about another, chances are you're looking at a stoichiometry problem. Okay, so we have our chemical equation, but of course we always want to make sure that the chemical equation is balanced. And of course, a balanced chemical equation has the same number of atoms on the left side as on the right side, or sometimes we'll say reactant side and product side. So just looking at this equation that we have right here, I've got 1 silver, 1 nitrate, 1 sodium, and 1 chloride ion. So this is a balanced chemical equation. We don't need to mess with it. Now that we know we're doing stoichiometry, we have a balanced chemical equation. This is where we're going to start doing our math. So let me switch over to my pen here. And I always like to start with what I'm given. And I was given 2 moles of silver nitrate. So I'm just going to write 2 moles silver nitrate. Okay, I'm going to be doing a lot of math here. I like to use the method that I call fence post, but some people like to write this in terms of multiplying different quantities. That's totally fine, whatever works for you. Now, we are already in moles, which means we can immediately use our balanced chemical equation. So again, I'm looking at my relationship between silver nitrate and silver chloride, because that's what the problem is asking me for. Now, what are the stoichiometric coefficients of those numbers? Well, nothing is written into the equation, but we always assume that when there is no number written in front of a molecule, it is a 1. So we assume that there is a 1 in front of our silver nitrate and a 1 in front of our silver chloride. So that means my mole ratio is 1 to 1. So for every 1 mole of silver nitrate, I will form 1 mole of silver chloride. Now, something I want to point out is mathematically this 1-to-1 ratio, it doesn't matter if you multiply by 1 first and then you divide by 1, or you divide by 1 and then multiply by 1. But it's very important when you're writing this out that your units cancel. So I'm going to switch to the red here. And you can see I started with moles of silver nitrate up at the top, and that is going to cancel with my moles of silver nitrate in the denominator. Again, mathematically for this problem, it really doesn't make much of a difference, but these are the habits you build for more complex problems so that later on you don't end up flipping a ratio. I see that error a lot. Okay, so going back to my blue, if I do this math, my moles of silver nitrate have canceled. That means I'm going to get out moles of silver chloride, which is exactly what the problem asked me. So this is very easy, of course. 2 moles of silver chloride. So this is a very trivial problem mathematically, but it does show how we approach all of our stoichiometry problems so that you get the method down so that it's easier to jump to the more complex problems. Okay, that's our first problem done. Let's do one more mole to mole problem and then we'll start doing some gram to gram. Okay, so our next problem is if 0.85 moles of carbon monoxide were formed, how many moles of carbon were used? Sorry, that should be were used. Anyway, what I am going to do is I'm going to first, of course, identify this as a stoichiometry problem. I am given information about one molecule, carbon monoxide. I am asked about another molecule, carbon, so I have to relate those with a balanced chemical equation. Of course, I already have my balanced chemical equation here, and here it's a little more obvious that yes, this equation is balanced. However, you can always double check that it is balanced, and one easy way to check is you can see I've got 3 carbon here. Well, do I have 3 carbon atoms on the right hand side, and I've got 2 here and 1 here. So yes, this is a balanced chemical equation. It's never a bad idea to check that it is balanced correctly. Okay, so let's start doing our math. Again, I'm going to start with what I was given. I was given that should be a decimal point, 0.85 moles of carbon monoxide. Now, again, just like before, because I am already in moles, I can jump right to my mole ratio, which I get from my balanced chemical equation. So I definitely need my stoichiometric coefficient for carbon monoxide. That is a 2 right here. And the question is asking me about moles of carbon. So carbon has a 3 in front of it. Again, that is its stoichiometric coefficient. When I'm writing this ratio down, again, this is where it's really important that you keep or set up your units such that the carbon monoxide cancels and you're left with carbon. So I'm going to put my moles of carbon monoxide in the denominator so that it'll cancel. I'm going to moles of carbon, and now I just put my numbers in my stoichiometric coefficients. Again, there was a 2 in front of the carbon monoxide and a 3 in front of the carbon. Let me switch over to my red. So again, my moles of carbon monoxide cancel. I am left with moles of carbon, which is exactly what the problem asked for. And I get 1.3, that's a decimal, moles of carbon as my answer. So again, mathematically, this one was a little more difficult, but you can see the methodology is exactly the same. Okay, so I assume that we're all good with mole to mole stoichiometry. Let's jump to something that's a little more difficult. Okay, so here is our next problem. Lithium oxide reacts with water to, that should be form lithium hydroxide. If 2.5 grams of lithium oxide react with an excess of water, how many grams of lithium hydroxide will be formed? Okay, so again, let's identify this as a stoichiometry problem. We are given information about one molecule, lithium oxide. We are asked information about another molecule, lithium hydroxide. We need a balanced chemical equation here. Obviously, we are given it right there. And so we have a chemical equation. Let's make sure it's balanced. Well, you can already see from the get-go, I have 2 lithium here and I only have 1 there. So this is an instance where you see the chemical equation and you assume it's just balanced. It's not always balanced. Always, always double check. That is, as a former teacher, that is one of the easiest tricks in the book. Okay, so to balance this chemical equation, I'm going to have to kind of squeeze it in. I'm certainly going to need a 2 in front of this lithium hydroxide. So now let's double check and see if we're completely balanced. I have 2 lithium, let's see, 2 lithium and 2 lithium. I have 2 oxygen here, 1, 2, 2 hydrogen. Okay, so this was actually a really easy one to balance, but again, always double check that your chemical equation is balanced. Now we're ready to start to do some math. Just like before, I'm going to start with what I was given. So I was given 2.50 grams of lithium oxide. That should be an I. Now I have a little bit of a problem here. I know I want to use my mole ratio, but I'm in grams right now. I can't use a mole ratio if I'm starting with grams. So my first order of business is going to convert these grams into moles. And the way we do that, of course, is with the molar mass. So I'm going to have in the numerator 1 mole of lithium oxide, and I do have this molar mass. This is 29.88 grams of lithium oxide. This is going to continue on for a little bit. So again, make sure that your units cancel. Let me switch over to my red. I started with grams of lithium oxide in the numerator, so that's why I put it in the denominator, so that these units cancel, and now I have successfully converted into moles of lithium oxide. The great thing is, now that I am in moles, I can use my mole ratio, I can use my balanced chemical equation. So I know that I want my moles of lithium oxide to cancel. The problem asked me to predict grams of lithium hydroxide, so I am going to be going to lithium hydroxide. Notice here, even though it asked me for grams, I'm only in moles here. This is a mole ratio. We will have to convert that moles to grams in a later step. Now I need my mole ratio. So, of course, we assume there's a 1 in front of this lithium oxide. So this is a 1. Oops, this is a 2. And switching back to my red. Now my moles of lithium oxide have canceled. I have converted to moles of hydroxide. Let me make that a little more clear. But the problem asked me for grams of lithium hydroxide, so I have one more step. I've got to convert this moles of lithium hydroxide to grams of lithium hydroxide. Again, I do that with the molar mass. So in the denominator, I'm going to have moles of lithium hydroxide. And I do have this molar mass. This is 23.95 grams per mole of lithium hydroxide. And again, you can see my moles of lithium hydroxide cancel. And my final unit is going to be grams of lithium hydroxide. So it's always good when your units cancel and the unit you end up with is the unit you want. That's always a really great sign that you've done the problem correctly. I always love those high signs, and I will put the answer down here. So running through this calculation, just with your calculator, you don't have to do this in your head, we will get 4.01 grams of lithium hydroxide. So you can see this one was a little more complex than just your mole to mole. We added a step at the beginning and at the end where we had to first convert grams to moles and then moles to grams. Now, before I started this problem, obviously I had already calculated my molar masses because I knew I would need them. That's another thing you can do when you do your stoichiometry problems, is before you start writing everything out, it's never a bad idea to go ahead and calculate your molar masses so those are ready to go. Okay, so looks like we're good with questions. Let's go on to our next problem. Okay. So this one reads, pure copper metal can be isolated from cuprite, which is Cu2O, by the following reaction. They give us a chemical equation. And if 150 grams of cuprite react, how many grams of copper do you expect to isolate? So just again, identifying that this is a stoichiometry problem, I am given grams of one molecule, the Cu2O. I am asked about grams of copper. That is a completely different molecule. I need a balanced chemical equation to connect these two molecules. Well, the great thing is we've got our balanced chemical equation right here. And again, just looking at it, I'm like, okay, good. Yes, we're balanced. That's fantastic. We can jump right into our math. So, just like before, I start with what I'm given. I was given 150 grams of Cu2O. This again is going to be a bit of a long one, so I'll give myself space. Now, because I am going to have to convert from the Cu2O over to the copper metal, I know I'm going to use my mole ratio, and right now I've got grams. So my first step is to convert grams of Cu2O into moles. And again, I have already calculated that molar mass, and that is 143.09 grams, again Cu2O, and so therefore my 1 mole is going to go in the numerator. Remember, when you're doing molar mass, it's always a certain number of grams per 1 mole. That is always true. So this one here is always going to be a 1 when you're talking about molar mass. That is different from your mole ratio where the numbers may change. Okay, so let's make sure that my units are canceling like I want them to. So my grams of Cu2O have canceled. I now have moles of Cu2O, so I can use my mole ratio to convert between molecules from Cu2O or cuprite to copper. So let's switch up and let's put in my mole ratio. So I know I want my moles of Cu2, oops, that should be a 2, to cancel. I am trying to predict moles of copper, again, per the problem itself. So now I need to know what the stoichiometric coefficient is in front of each of those molecules. So I have a 2 in front of my Cu2O, and I have a 4 in front of my copper. So that is my mole ratio. Until you get really comfortable, I do like putting these numbers in after you've put your units in. Again, it's really, really common to get these ratios flipped. And then obviously here, instead of in general multiplying by 2, you'd be dividing by 2, and then it's very frustrating when you get that answer wrong. Okay, so let's first show that my units have canceled like I'm expecting them to. So there's my moles of Cu2O, and it is canceling there. Okay, great. Now I have moles of copper, but of course the problem has asked me for grams of copper, so I have one more step, and that is to convert my moles of copper here into grams of copper. At least this molar mass you can really just pull from the periodic table. and that is 63.55 grams per 1 mole. Okay, again, just for completeness sake, that cancels. My final unit is grams of copper. Yes, that is what the problem asked me for. So I have some confidence that I have answered this question correctly. So here again, you would plug and chug through your calculator, which I have already done, and you will get 133.2 grams of copper. Okay, I'm going to give just a little pause here, check the comments, see if there are any questions. Okay. Okay, great. It looks like we are all set there. So let's move on to my next question. Okay, so next question, we've got some baking soda. All right. So when baking soda is heated, it forms sodium carbonate, water, and carbon dioxide. This is an example of a decomposition reaction. Yes, very true. If 75 kilograms of carbon dioxide were formed, how many grams of baking soda decomposed? Okay, so this is a gram to gram with a little bit of a twist because we've got kilogram right here, but not too much of a twist. Okay, so again, identifying this as a stoichiometry problem. You can see like I go through the same steps every time. That always helps me when things are very systematic, because then I can be confident that I'm doing the problem right because I can check my boxes. I've done step 1, step 2, step 3, etc., etc. So how do I know this is a stoichiometry problem, except for the fact that I'm doing all stoichiometry problems? I was given information about carbon dioxide. I was asked about baking soda, so I've got to connect those two molecules with, again, a balanced chemical equation, which the problem was very nice to provide right up here. Again, just do a quick check. Looks like we're all balanced. We're good to go, so we don't have to balance anything. That's fantastic. And now we're just going to start working through the math. Okay, so again, my next step, starting with what I was given. I was given 75 kilograms of carbon dioxide. Okay, so 75, that 5 is a little wonky, there we go, kilograms of carbon dioxide. So previously I just converted grams to moles. Well, again, this is the twist here. I've got kilograms. So first what I need to do is convert my kilograms into grams, and then I can convert it into moles. So this is just a simple conversion. In 1 kilogram, there are 1,000 grams. Again, making sure everything cancels. So my kilogram cancels with my kilogram, and now I'm left with grams. And really, I should be specific here and make this grams of carbon dioxide and not just general grams. Because otherwise someone looking at this problem would say, well, grams of what? Are you already at grams of baking soda? I don't know what. So that is grams of carbon dioxide. Okay, now that we've got grams of carbon dioxide, we need to convert to moles of carbon dioxide because, again, eventually we're going to use this mole ratio. Mole ratio means you have to be in moles. So I need to get this grams of carbon dioxide canceled and converted into moles of carbon dioxide. Of course, we do this with the molar mass. So this will be a mole in the numerator. And my molar mass for carbon dioxide is 44.01 grams of carbon dioxide. That is a 1 there. And let's just show all our canceling. So grams of carbon dioxide is now out. Now I've got moles of carbon dioxide, which means I can now use my mole ratio. I'm going to need more space here. Okay, so I know that I want my moles of carbon dioxide to cancel. The problem, let's see, is asking me for grams of baking soda, which is this guy right here. So here is my molecular formula for baking soda. Now I need my stoichiometric coefficients. Let's see, in front of the carbon dioxide I just have a 1. Again, remember that's assumed to be a 1. And I have a 2 in front of my baking soda, so that is set. Again, making sure that my units cancel. So now, so far, I've converted everything into moles of baking soda. But of course the problem asks me for grams, so I've got one more step, and that is to convert moles of baking soda into grams of baking soda, and I do that with the molar mass. Oops. Okay, so there my moles of baking soda go in the denominator, and my molar mass of baking soda is 84.007, that's a 7 grams. Let me make that decimal point a little more clear. And of course this is baking soda. And for completeness, we can see that my moles of baking soda cancel. I am left with grams of baking soda. I always like to see the unit I expect come out. And if I run this through the calculator, which I have already done, I get a whole lot of grams of baking soda. That's really illegible right there, isn't it? Okay, that is a 6. So 2.86 times 10 to the 5th grams of baking soda. But you would expect a large number. We did start with 75 kilograms of carbon dioxide. So I would be worried if that came out as 2.86 times 10 to the negative 5th, and I'd worried I had something flipped there. Okay, so let's check comments, make sure that everything looks okay here. Okay, it doesn't look like we have any questions, so we will move on to our next problem. Okay, when ethanol undergoes combustion, it forms carbon dioxide and water vapor. How many grams of water vapor form when 65 milliliters of pure ethanol burn completely? And it gives us the density of ethanol as 0.791 grams per milliliter. Okay. So again, this is a stoichiometry problem with a twist. This is one that includes density. So really we're doing a stoichiometry problem that's we're gonna go from a volume to grams. All right, so again, let's just identify it as stoichiometry. Let's see, we were given 65 milliliters of ethanol, and we are asked about how many grams of water vapor. Again, we need a balanced chemical equation to connect these two molecules, and thankfully they have already given it to us, especially when it's a combustion problem. Sometimes those are very easy to balance, and sometimes they can be a little tricky to balance. So it's nice that we've already got that there. Okay, so just like before, although I'm probably going to have extra steps, so I need to make sure I start to the far left. Let's start with what I was given, and I was given 65 milliliters of pure ethanol. So 65 milliliters of ethanol, H6O3. Okay, make that decimal a little more clear. Okay, so I know that I'm going to use my mole ratio at some point because I've got to switch over from ethanol to water vapor. So here is where I kind of start to work a little bit backwards from that. So I know I want to eventually get to moles of ethanol. I've got to get to that to use my mole ratio. And it's been pretty easy to convert grams to moles. I just use a molar mass. but I'm starting with milliliters. So again, I'm thinking backwards. If I have moles, I know I can go grams to moles, but how can I get from milliliters to grams? Well, a hint is what the problem gave you. So the problem gave you a little bit of extra information, and that is the density of ethanol. And you can see in the units here, it's grams per milliliter. So that means I can use density to convert either grams to milliliters or milliliters to grams. It lets me go either way. So because I have milliliters, I can use the density to convert to grams, and then once I'm in grams, I can use the molar mass to convert to moles, and then I'm ready to use my mole ratio. So in these kind of problems, sometimes I will kind of step back from the mole ratio and think, how can I get back to my starting point? Again, different people kind of have different thought processes, so you might find that you do a completely different thought process. It really doesn't matter as long as you end up with the same answer in the end. Okay, so again, I've already written down what I was given, my 65 milliliters of ethanol. I am going to use my density to convert that into grams. Now, I want to be careful that I put the density in the right way, so I'm going to put my units in first. I want my milliliters of ethanol to cancel, so those need to go in the denominator. And of course, if milliliters are in the denominator, that means grams are in the numerator. And now I do my numbers. So it is 0.791 grams per 1 milliliter. And this way I can make sure that I am, like here, I'm going to be multiplying, and you don't want to actually switch that and be dividing. So my milliliters of ethanol cancel. Now I have grams of ethanol, and now I'm feeling much more comfortable with my next steps, because once I have grams, then I know I can convert to moles using the molar mass, which of course I already have, and that is 46.07. Okay, so that's grams of ethanol per 1 mole of ethanol. Okay, again, let's make sure that this has canceled like I want. So yes, grams of ethanol is canceled. Now I have moles of ethanol. Now I'm ready to use my mole ratio. So I know that I want my moles of ethanol to cancel. And let's double check. The problem asked me for grams of water vapor. So I'm going to want to go to moles of water. And now I just need my stoichiometric coefficients. So again, we assume there's a 1 in front of the ethanol here. And for the water, there's a 3 there. So that is my mole ratio. Again, let's cancel. So now I don't have moles of ethanol anymore. I have moles of water. I'm running out of space on that line, so I am just going to continue down here. Because I need grams of water, I just need 1 more conversion factor, and I need my moles of water to be converted to gram. So I'm just using the molar mass, and that is 18.015 grams of water per 1 mole of water. Again, my moles of water cancel. I'm left with grams of water, which is exactly what the problem asked me for. So if I run this through my calculator, I am going to get 56. Oh, that 6 is a little wonky. Okay, 56.6 grams of water, and we can even put the gas symbol there for water vapor. So these problems where you throw in density do tend to throw students initially. Again, I like to focus in on, I know I'm going to use my mole ratio, so how can I set up my conversion factors so I can either get 2 moles Or again, I like to think about working backwards. So how do I get back to milliliters? Again, it's just whatever makes the most sense to you. That's the method that you want to use. So before I go on to the next problem, I just want to double check comments and make sure that everyone is still with me. And it looks like we're good. All right. So let's go on to our next problem. Okay, so this one reads, a unique way to produce formic acid is shown below. If 93.5 milliliters of formic acid was produced, how many grams of iron sulfide was consumed? The density of formic acid is 1.22 grams per milliliter. Okay, so the problem gave us a huge hint here. It gave us density, so we know we're going to have to throw that density in somewhere. But as usual, let's identify this as a stoichiometry problem. I kind of skipped that, didn't it? Okay, so we know that 93.5 milliliters of formic acid was produced, so that is what we have been given. We have been asked about grams of iron sulfide, so we need to connect those two molecules with a balanced chemical equation. Here is our chemical equation. Now, it's looking like it's either all 1-to-1 ratio or maybe it's unbalanced. So let's just take a look really quick. I've got 2 hydrogen, 2 oxycarbon. Okay, so this actually is looking like it is balanced. It's all just a 1-to-1 ratio. Whenever I have a problem that is all 1-to-1, I always am going to have a knee-jerk reaction and say, wait, is that actually balanced or not? But that is a balanced chemical equation. Okay, so we've got a stoichiometry problem. We're going to have to use density. I always like to go ahead and write down what I was given. Sometimes, especially when I was in a test situation and I was already kind of nervous, just writing something down really helped me focus in on how to do the problem. So I still always do that. I write things down first. So I was given 93.50 milliliters of formic acid, and I forgot my carbon there. So CH2O2. This is going to be another long one. All right, so I'm going to use a mole ratio. I've got formic acid. I've got to get to iron sulfide. Here is my balanced chemical equation to do that. So just like before, I kind of think backwards. I'm going to need moles. I need to get my milliliters of formic acid into moles of formic acid. I don't have a one-step way to do that. I'm going to have to do that in 2 steps. And that is, I'm going to use the density first to convert from milliliters to grams. And then once I'm in grams, I can use the molar mass to convert to moles. And then I'm at my mole ratio. So let's get those steps in. So just to make sure I put my density in correct, I do like to often put my units in first and then put my numbers in. So if my milliliters are in the denominator, it means my grams must be in the numerator. Okay, this is going to be 1 milliliter and 1.22 grams of formic acid. Okay, let's make sure everything cancels like I want. And my milliliters of formic acid cancel, and I've got grams of formic acid. Okay, perfect. Now for my next step. Now that I've got grams of formic acid, I am going to use my molar mass to convert to moles of formic acid. So I have this molar mass, and here it is. That is 46.003 grams of formic acid and 1 mole of formic acid. My pen is just not cooperating anymore, is it? There we go. Okay, So let's cancel out my grams of formic acid. Now I have moles of formic acid. Now I am ready to use my mole ratio. So I know that my moles of formic acid are going to be in the denominator. Let's see, let's double check. The problem is asking me for iron sulfide. So that is going in my numerator. Again, this balanced chemical equation was, everything was a 1-to-1 ratio, so that makes this really easy. And I'm going to continue on here down below because I ran out of space. And let's make sure we cancel moles of formic acid. Now I have moles of iron sulfide. And yes, the problem wants grams. So I have one more step. I need to use the molar mass to convert moles of iron sulfide into grams of iron sulfide. So I need my moles to cancel. And let's see, my molar mass is 87.91 grams per mole. Make sure that everything has canceled like I want. And I'm left with grams of iron sulfide, which is what the problem asked for. So now I can run this through my calculator, and you will get 217.9 grams of iron sulfide. And let's make that decimal a little bit bigger. Okay, so again, this was a multiple number of steps. I always like to see that everything has canceled except for my very last number here. That always is very satisfying to me. Before I go on to any more problems, let me make sure that everything is set. Okay, all right, that is fantastic. And let's go on to our next problem. Okay, so a reaction of lead nitride and potassium iodide forms lead iodide and potassium nitrate. If 75 grams of lead iodide formed, how many milliliters of a 0.75 molar solution of potassium iodide was used? Okay, and there is our chemical equation. This one is going to be the same, but again, a little bit of a twist. So we have been given information about lead iodide, and of course we're asked about potassium iodide, so there's our connection that it is a stoichiometry problem. We need a balanced chemical equation, and the nice thing is there is our balanced chemical equation right there, and then they've even got the states in. Now for this problem, we have concentration. So again, it is a stoichiometry problem. A lot of things are going to be the same, but because we have concentration, there are going to be some things that are a little bit different. But just as before, I like to start with what I was given. So I was given this 75 grams of lead iodide. Now you might ask, why am I not starting with my concentration? Well, because this concentration is given to me as part of the information that's given, but I want to know how many milliliters of that solution, so it is not complete information. Whereas my 75 grams of lead iodide, I can start with that and I have no questions except for what do I need to convert that into. However, if you're not sure which one to start with, just pick one. Start with it, see if you can move forward. If you can't move forward, then go back and use the other piece of information. Guess and test is never a bad thing to use. Sometimes it works great. Okay, so here is my 75 grams of lead iodide. Okay, I'm sure I'm going to need lots of space here. But this is a stoichiometry problem. I'm starting with grams. I know I'm going to use my mole ratio, so I am just going to kind of chug along like I've done with my other problems. I'm going to convert grams to moles, and then I'm going to use my mole ratio to go from my lead iodide to my potassium iodide. Okay, so I've got grams. Let's use molar mass here. So this is going to be 1 mole of lead iodide. And I do have the molar mass. Here we go. 461.01 grams of lead iodide per mole. Yes, it has a very large molar mass. Okay, let's make sure everything canceled like I wanted it. So my grams of lead iodide canceled. Now I've got moles of lead iodide. Now I can use my mole ratio to convert between molecules. So I'm going to, I know I want my moles. That is a moles of lead iodide to cancel. And the problem has asked me to go to potassium iodide. That was not a very good M. Let me check my balanced chemical equation. Okay, I assume I've got a 1 there in front of lead iodide, and there is a 2 in front of potassium iodide. And that did not really write very well, did it? That's better. Again, making sure things cancel, so my moles of lead iodide cancel. Now I have moles of potassium iodide. Now that I am in potassium iodide, now I'm going to need to deal with concentration. Okay, so let's do a little bit of review here. When you have concentration and you have molarity, remember that molarity is your moles of solute over your liters of solution. Now, in our case, it's going to be moles of Ki, or potassium iodide, over liters of solution. So the nice thing is we've already got moles here. We don't need to convert to grams. Now again, if you're working through this problem and you're just kind of on a roll and you go to grams, that's fine. What you'll end up doing is converting back out of grams into moles, but you know, you don't have to. I can save you a step by saying you're already in moles and we're going to be using moles in our concentration, so let's not convert to grams. Now, your molarity here can be used as a conversion factor because it is moles per liter, and I have moles here, so I can use this to cancel out my moles of potassium iodide. So what I'm going to do is I'm going to have my moles of potassium iodide in the denominator, which means my liters of solution go in the numerator, and now I just need numbers. Well, I was given that it was 0.75, and that is going to be 0.75 moles of potassium iodide over 1 liter of solution. So what I have done here is my moles of potassium iodide have canceled, and now I have liters of solution. So now I'm really close to having my answer because I have liters and I'm looking for milliliters here. So my last step is simply to convert from liters to milliliters. And I think I can even fit it all on this line. So in 1 liter of solution, there are 1,000 milliliters of solution. And again, I should be more specific here. This is liter of solution. Specifically, this is the potassium iodide solution. Let me just squeeze that in here. Let's make sure I'm canceled. Yes, my liters of solution cancel. Now I'm left with milliliters of solution, and again, the solution is potassium iodide, which is exactly what the problem up here wants. So I just run this through my calculator, and I am going to get 434 milliliters of potassium iodide. There it goes. And that is a solution. Now, another way to approach this problem is to drop this part of it. End the problem here. Calculate your moles of potassium iodide. Plug it into this concentration formula, plug in your 0.75 there, and solve for liters of solution. It will get you the exact same answer. So a lot of these kinds of problems mathematically you can break up into different steps if you want, and that is perfectly fine. Again, all that matters is you find a way to get the correct answer that makes the most sense to you. So you don't have to, I call this kind of smashing a problem together. I like to line up all of my conversion factors and just put it into my calculator once, but you don't have to do it that way. You can always break it apart in a way that makes the most sense to you. You don't have to do it in one big calculation. So because this was our first concentration, let me just make sure that there aren't any major questions here before we go on to the next one. And it looks like, well, yes, there are. OG Benchmarks asks if there is anything that you can't calculate, and there are plenty of things that you can't calculate. But for these problems, thankfully, we can calculate just about everything. Okay, I think we've got time for at least one more problem. Let's see what we've got next. Okay, so this one reads 0.15 grams of calcium sulfate was isolated from the reaction of calcium chloride and sodium sulfate. The other product was sodium chloride. What was the original concentration of sodium sulfate if 75 milliliters was initially used? Okay, so we've got another concentration problem. So I'm glad that we're going to be able to get one more concentration problem in before the hour is up, because these can be difficult, and you have to, for me, I had to see them a couple times before I really got comfortable with them. Okay, so let's first, as usual, identify this as a stoichiometry problem. So we were given grams of calcium sulfate, and we were asked for the concentration of sodium sulfate. So we've got two different molecules. We need a balanced chemical equation to go in between these. And here is our chemical equation. Let's just double check and make sure we are, yes, we are balanced, and we've got our states. So this is a precipitation reaction, which makes sense. So we obviously isolated our precipitate from this. Okay, but I digress. Let's start with what we were given. So we were given our 0.150 grams of precipitate, calcium sulfate. Okay, so I know I'm going to use a mole ratio here. I've got grams, so getting to moles is pretty easy. So let's go ahead and convert to moles and then put our mole ratio in, and we'll deal with the concentration side in a little bit. We don't have to deal with it right now. So I've got grams of calcium sulfate to convert to moles. I need the molar mass. I do have that molar mass. Here it is, 136.14 grams per mole. And this is 1 mole calcium sulfate. Okay, great. Let's make sure everything cancels like I want. Yep, my grams are gone. Now I've got moles. Now I can use my mole ratio. I know that I want my moles of calcium sulfate to cancel. So I'm going to put that in the denominator. Let's double check. What am I going for? Sodium sulfate. Okay. Okay, so now I've got my units in. Let's get my stoichiometric coefficients. Let's see, calcium sulfate. Okay, I'm assuming there's a 1. And sodium sulfate. Okay, so it's a 1-to-1 ratio. That makes everything really easy mathematically. But you can see that my units still cancel. Okay, so again, we want concentration. We're given a volume. So I know I'm going to use, let me just go green here, again, my molarity. In this case, it's going to be my moles of solute, which is sodium sulfate, over my liters of solution. Again, I like to use it as a conversion factor, but you don't have to. You can end the calculation here, and you can plug in your moles, and you can plug in your volume and get your molarity. That's perfectly fine. Or you can do some smashing, which is what I do. So I'm going to use it as a conversion factor. I have 75 milliliters. Now I'm going to go ahead and convert that into liters. So that is 0.075 liters of solution. Again, this is the solution of sodium sulfate. And for this one, I'm just going to put a 1 in the numerator. There is no other unit that goes with it. I'm just dividing by my liters. And this gives me my concentration, which is 1.47 times, yeesh, that did not work out, times 10 to the negative second, and that is molarity. And the one thing I do want to point out here is, remember, molarity is moles per liter. So do I have that in my units? And I do, because here are my moles, here are my liters. So in our previous problems, I canceled out all of the units except for the last one, the one that we were going for. But in this case, because I have molarity, I actually need to keep 2 units. It needs to be moles per liter. So that's why I have moles of sodium sulfate over liters of solution. And again, the solution is also sodium sulfate. So it's really important that your units are matching with what your answer is going to be. But just like I said before, you don't have to smash this calculation together. You can cut it off right here. Use your formula for molarity and calculate your concentration that way. Both ways will give you the exact same answer. Okay, let's make sure there are no other questions. It doesn't look like there are any other questions. I do hope that you found working these problems together is helpful. Sometimes I know when I was coming along, I like just seeing people work the problems. How do you handle this kind of problem? How do you handle density? How do you handle concentration? How do you handle gas laws? There are lots of different kinds of stoichiometry problems out there. So I do hope you found this helpful. So the plan is to do another live stream next Wednesday. Again, it'll be 7 p.m. Eastern Time, which is 4 p.m. Pacific Time. If you have questions that you want me to work specifically, please email me. You can email me at karen@chemhelpasap.com. That email is also on our YouTube page, and it's also on our website. So because I didn't get through all of our stoichiometry problems, like I didn't even touch on gas laws yet, my plan is for next week to do another live stream with more stoichiometry problems, because I know that's probably where a lot of classes are right now. But I do want your feedback. If you want other topics covered, please let me know, and we can work problems in any general chemistry topic that you would like. So thank you very much for joining me for the live stream, and I will see you next week.